Hey there, awesome physics students. Let's talk about angular motion. Before we get into the nitty-gritty details, let's talk about an example in track and field. So if you run around a track once, that's 400 meters. But is it an advantage to run around in the middle lane versus the outside lane? Well, before we answer that, let's think about something rotating through part of a circle. So let's draw our x and y axis here. So here's our y-axis and our x-axis is here. So imagine starting at the positive x-axis and rotating up to an angle theta here. And the radius of that we're going to rotate through is r. There's our angle theta. And when we do that, if we start at this point here, we're going to travel through a distance s from the axis that's going to be part of a circle. Now, if we had started closer to the axis of rotation, which is at the origin, our radius of our circle that we would trace out is smaller, and we would also travel a smaller distance s. So what is the relationship between s, r, and theta if you're just traveling through part of a circle like this? Well, the connection here is the so-called arc length formula, and that is s is equal to r theta. Now this says a couple of different important things. First of all, it says that as you increase your distance r from the axis of rotation and you travel through the same angle, then the distance you'll travel through that part of the circle, s, will be bigger. So that explains why these two lengths were different lengths, even though they're still part of the same angle. It also says that if you, of course, travel through a bigger angle on the same circle, if I were to keep traveling here, this s would be bigger, but my angle theta would also be bigger. So that tells you a relationship between s and theta. It also defines what a radian is. To use this equation here, you have to have theta in what are called radians. Now, radian, if I just rearrange this equation here and divide both sides by r, then that will give me theta is equal to s over r. So what this says is this is a radian, and a radian is just the ratio of the arc length that you move to the radius of the circle that you're traveling part of. It's just a ratio. So really, radians are not a unit on their own. They're really just a ratio of arc length to radius. By the way, an angle of 1 radian would be where the arc length s is about equal to the radius r. So that's about like this smaller arc length here is about equal to 1 radian. So that angle is about equal to 1 radian. By the way, if you go once around a circle, that's 2 pi radians. That is the same as going around the circle once, which is 360 degrees, which is the same as 1 revolution going around the circle once. By the way, you've probably used this without even realizing it. So let's think about a situation here where you go around in a circle once, and in that case, of course, the angle, like I said before, was 2 pi radians. But what's the distance around the circle in this case? That would be s. Well, this equation says I take s is equal to r times theta, so theta is 2 pi. This is telling me that the distance around the circle is 2 pi r. Well, that's just the circumference of a circle. That's the equation that you've used before, and probably in middle school, for the circumference of a circle. It's really from this equation. In fact, this is a generalization of that equation. Let's think finally about something that's more practical and more physically significant for us. If you walk, as you walk, your feet go through an arc length down here that's much larger than the arc length that your knees will travel through. Well, why is that? Why do your feet travel a bigger distance? Is that because they travel a bigger angle, or is it because of the r, the radius of the circle they travel through is bigger? Well, the axis of rotation is here at your hip, and so the distance that your knees are from the axis of rotation, that would be r. That is smaller than the distance from your hip to your feet. And so yes, the radius for your knees is going to be smaller, therefore the arc length is going to be smaller. Of course, we don't actually walk this way with our knees unbent like Frankenstein or something like that. The way we actually do it here is let's say we're running, we're trying to go quickly, what you actually do is you bend your knee, right? And so when you swing your knee through some arc length here, when you bend your knee, you're actually bringing your foot closer to the axis of rotation. And that reduces R, which means that the arc length S that your foot has to travel through is much reduced because it's closer to the axis of rotation there. And so you can actually gain some efficiency by doing that and move your foot through a smaller physical distance. All right, so hopefully this gives you an overview of the connection for angular motion. The big thing here is to remember the arc length formula, and most everything connects back to this.